Hi everyone, I'm Bhushan Suwal, and along with my co-author J.N. Matthews, I'm going to be presenting our joint work with Aloni Cohen and Duchin on the impacts of the Census Bureau's differentially private disclosure avoidance algorithm top-down on redistricting. The census is an enumeration of all the people living in the country, and it takes place every 10 years. The primary purpose of these numbers are for apportionment and redistricting. Why is the census using differential privacy? So the US Census Bureau performed a reconstruction attack on its 2010 release and re-identified 17% of the US population. They took the aggregated data, like in the table on the left, and reconstructed individual data, as in the table on the right. Then they combined the results with commercial datasets and showed that individuals could then be de-anonymized. Now, Title 13 of the US Code forbids the census from publishing any data where the individuals in the data can be identified. The Census Bureau concluded that the disclosure avoidance techniques used in 2010 were inadequate for 2020. This is why the census is using DP as its privacy protecting mechanism.
So, what are people's concerns about noisy census data? The census has a lot of use cases. Often the data is used to allocate state and federal funds and resources. And if small population areas become indistinguishable from noise, local municipalities might not get the resources they need to serve their communities. While this is an important consideration, this use case isn't the one enshrined into law via the establishment of the census. The constitutional basis for the census is congressional apportionment. It was created to figure out how many representatives each of the states should receive in Congress. That constitutionally grounding has been later interpreted by the courts to mean that each member of the House is to be elected by a single member district and that those districts need to be of equal population size. This is the one person, one vote doctrine. To facilitate this, the census releases the PL 94 for redistricting each decade. This includes population, race, ethnicity, and age, all broken down by counts at the census block. At the federal level, districts need to be population balanced and compliant with the Voting Rights Act, although states can set other rules as well, such as contiguity and compactness. The Voting Rights Act was signed into law by Lyndon B. Johnson in 1965. It is one of the most significant pieces of civil rights legislation in U.S. history and has been continuously expanded by Congress. Broadly speaking, it secures the right for minority groups to elect candidates of their choice. There's been a large amount of court precedent determining how the VRA is enforced. One of the major such cases is Thornburg v. Jingles, which set forth a checklist of things to show in order to bring forth a VRA challenge. These are called the Jingles factors, and we'll talk about them in more details later. How is the census going to be adding differentially private noise? In order to talk about the algorithm used to add this noise, we first need to talk about how the census releases its data. The census releases counts that are associated with geographies. These geographies scan scales from across the whole nation to a single city block. The center core here is called the census spine. Each of these geographies subdivide the ones above them. Census blocks are the smallest units. You can see them in the small purple outlines. Groups of these blocks form census block groups, which are outlined in darker purple, and groups of these block groups form census tracts, which are outlined in pink. The census spine is how this data is released, but they're not the only geographies that matter. Notice that congressional districts and voting precincts are built out of blocks, but only directly nest into states and counties, respectively. We'll call these off-the-spine geographies. Census data also has a bunch of implicit constraints. The most stark might be that 40% of all census blocks are empty and don't have any population. Constraints such as these empty blocks define a feasible space of potential noisy results. The differentially private algorithm that the census is using is called top-down. The noise is drawn with respect to a parameter called the epsilon budget, which defines the amount of noise added. At 0, the results have total privacy and are just noise, and as epsilon approaches infinity, the results are more and more accurate. Noise is added sequentially to the levels of the census spine, from largest to smallest. We'll start with the population totals for the whole nation. We then add noise to the national level with respect to the epsilon budget at the national level, and adjust the closest spot in the feasible space. Now, for each of the states that subdivide the nation, we add noise and adjust them. Note that this adjustment step accounts for the national level results, so that means that the sums of all the results across the states are consistent with the national totals. This is then applied top-down, level by level. Notice that each level has its own portion of the epsilon budget, and that the epsilons across all the levels sum to the total epsilon budget.
There are three main questions we ask in our work. Number one, the census data is used to launch Voting Rights Act cases in court. There are certain methods that use these data that the courts are familiar with. How will DP affect these methods and consequently these cases? Second, How much error will top-down introduce to population totals in districts or in census blocks? Finally, how does the allocation of epsilon affect the results? Again, remember each level on the census hierarchy could be allocated different epsilon values. How would changing the relative proportion of the epsilon across the levels affect the error in our districts and the VRA cases? Broadly, there were two ways we approached this. Experimentally, we ran top-down for our experiments on reconstructed data. We also developed a simpler version of top-down that we call toy-down, which we study analytically and also run experiments on. I will further expand on toy-down in a bit. A note here that studying top-down is a moving target. We used the 2018 end-to-end version on GitHub for our experiments. The census has since made many improvements to top-down in the last couple of years, but the final code that they are going to eventually use has not been made public yet. So to run our experiments, we needed data. Census only releases data after 72 years, so the most recent public data is from 1940. We used reconstructed data from 2010. For this, we received help from Mark Hansen's team, who developed and shared the reconstruction code and data with us. As I said earlier, we want to see how the different allocations of epsilon affect our error. In our experiments, we use 4 different total epsilon budgets from 0.25 to 2, and then use 4 different ways of splitting the budget across the levels of the hierarchy. For example, in the equal allocation, we give each level the same epsilon. In the block-heavy allocation, we allocate relatively more epsilon to the blocks. In the tract-heavy allocation, we allocate relatively more to the tracts, and then for the county-heavy allocation, we allocate more to the counties. And lastly, to simplify studying top-down, we turn off the household constraints, which has the effect of reducing the workload. I'm next going to explain toy-down, our simplified model of top-down. Here you have a toy example of 3 levels in the hierarchy. And let's assume that each number is the total population at that unit. Notice that the parent node is the sum of its children, which we will call hierarchical consistency. The first step is to add Laplace noise to each unit. As this is top-down, you first noise the red unit, and then the green units, and then the blue units. But notice now that we are no longer hierarchically consistent. The parent is no longer the sum of the children. So we have an additional post-processing step that makes the tree hierarchically consistent again. Following top-down, we start at the top and work our way down the tree, enforcing consistency. After post-processing, the noise at the upper level affects the lower levels, and we want to understand it. The 2 stages of toy-down are modeled after top-down. Like top-down, toy-down maintains hierarchical consistency and optionally requires positive populations. But it doesn't capture the other knobs in top-down, like household constraints. And it doesn't capture the larger workload in top-down, which includes attributes like age and sex, among others.
Okay, so now let's talk about our results. One of the benefits of toy-down is that it is a simple enough model for a pen and paper analysis. We can derive closed form expressions for the mean and the variance of a geography given the hierarchical structure, and this is true even for off-the-spine geographies like districts. For example, here's the error variance of a geographic unit on the census spine, say a census block or a tract. Don't worry about exactly what this expression says. I haven't even explained the notation. The point is that we can write this down and understand how it behaves. One of our goals was to understand how to allocate the epsilon budget across levels. Here we plot the previous equation for the area variance for a simple 3-level hierarchy. For example, the diagram in the bottom right, similar to the trees Bhushan showed earlier. On the y-axis is the variance at the block level, or the blue nodes in the hierarchy diagram. The line color shows the percentage of the weight at the bottom level. So the top blue line is where the bottom level has 10% of the epsilon budget, and moving down, the orange line is where it has 20% of the total epsilon budget. And they start to bunch up as you go down. The x-axis shows the percentage of the remaining budget that's given to the top level. Close to 0 is where the second level in the hierarchy has most of the remaining epsilon budget, and close to 1 is where the first level in the hierarchy has most of the remaining epsilon. Notice that while there is some error propagation from higher levels, it is only in the extremes. It's when there's a large discrepancy in the budget among previous levels that we see this error propagate. And for the most part, the error variance of the block is dominated by the epsilon budget at that level. Once we get to the red line, which is around 40% of the total epsilon at the bottom level, all of the lines are closely bunched together. The curves are also quite flat-bottomed across the x-axis. Putting these together, we can see that there is a wide range of epsilon splits that would result in a reasonably low error variance. In order to minimize the error variance at the block level, we want to put most of the weight at that level. The minimum for this hierarchy in particular is where we put around 80% at the block level, and we find something similar holds true in our experiments with top-down. However, this is with respect to errors of the census spine, and we see something different when we build districts which are off the census spine. So how much error do we see at the district level? Each one of these histograms has 1,000 values. To generate each value, we draw a district. You can see some example districts for Dallas County shown in yellow. The rest of the county is colored green. And then we compute the district's population over 16 runs of top-down. The plotted value is then the mean of the on-site population error for a district across those 16 runs. There are two methods of drawing districts shown here. Recom, which is the top two districts, builds reasonably compact districts, and Discon, which is the bottom two districts, randomly samples units until population balance is reached without regard to contiguity or geography. Of these methods, the blue one, block recom, matches most closely with enacted plans. And if you're going to follow one thing in the next couple of slides, look at the blue histograms. Notice in the histograms that all the districts have errors in the hundreds to thousands range, although they do differ by method. There are two parameters at play here, and the differences by methods. There's the size of the building block. Here we're using tracks, which are the left districts, and blocks, which are the right districts. And the contiguity/compactness of the districts, here, which is recom versus discon. More detailed findings about these influences can be found in our paper. Okay, so there's a lot going on this slide, and I don't expect you to follow all of it, but we'll walk through some of the key points. The circled figure is the one we just saw, where we ran top-down with equal allocation across the four methods, drawing districts of around 600,000 people. The rest of the histograms are of the same four district drawing methods from the previous slide, but varying the budget allocation, noising algorithm, and district size. The left half of this figure is with respect to districts of around 600,000 people, and the right half of the figure is with respect to smaller districts with around 16,000 people per district. Each row is a different allocation of the privacy budget, and the columns are different noising algorithms, so top-down versus top-down. Compare the circled figure, which has equal allocation, to top-down with a block-heavy allocation. Notice that while the orange histogram, which is block discon, has less error, it's more left on the bottom square, all the other ones have more or the same error with a block-heavy split versus an equally allocated split. And this holds true even for the smaller districts. We've seen before that weighting the block level more heavily produces more accuracy at the blocks, but we also care about the error in these larger off-the-spine units, and it looks like an equal allocation of budget here is a better trade-off once we account for the contiguity of these units.
Now we turn towards investigating how the noise affects Voting Rights Act cases. The Voting Rights Act protects minority voting rights. To launch a VRA case, there is a three-part checklist criteria called the Jingles criteria. For this project, we focus on Jingles 2 and 3, which in conjunction ask, do the majority and the minority vote differently? And if so, does the majority block the minority's preference? Specifically, the court requires you to back up a statement like, this population strongly supports this candidate. One method that does this is called ecological regression, which I will explain in more detail. Despite its simplicity, ecological regression has a history of court precedent and is a routine procedure in bringing forward a VRA case. So ecological regression. This is a figure for support for Valdez in the 2018 Texas governor election. Each blue dot is a precinct. On the x-axis is the percent Hispanic population, which we get from the census. On the y-axis is the percent of voters from that precinct that voted for Valdez. The blue line is a line of best fit. Remember, the goal is to say that Valdez has X% of Hispanic support. That is done by looking at the point where X equals 1, where this regression tells us that a precinct with 100% Hispanic population would vote for Valdez, in this case, about 85% of the time. Similarly, at X equals 0, when there are no Hispanic people in the precinct, ecological regression says that Valdez would get about 60% of the support. This is the non-Hispanic support for Valdez. And these are the two main estimates this regression gives us. So far, no noise has been added. This is what it looks like when you add noise. There is a lot happening in this slide, and I will explain it slowly. This is the same data as in the last slide, but this time we have run toy down on the data. We ran toy down 16 times, and the noise numbers are in pink. After each noising run, we again draw the line of best fit for those noise numbers, this time coloring them in red. We can see that at x equals 1, the ecological regression estimates change substantially than that of the blue line. I want to draw your notice to the precinct encircled in green that has a significant change in the percent Hispanic population. It implies that the Hispanic population in that precinct was low, so the noise changed the percent population by a lot. In contrast, notice the precinct encircled in purple. The noise has not moved this point a lot, implying that the Hispanic population here was large, and the noising did not make substantial changes to the percent population in that precinct. Finally, notice that the pink dots in the plot only move horizontally, because only the census data is being noised. The y-axis is election data that is reported definitively and is untouched by toy down. This is the same data, but noised by top-down. What we see is that top-down and toy-down both affect the standard ecological regression analysis. As I'll explain next, a small change to ecological regression makes this effect almost disappear. On the left is the figure we just saw on the last slide using the standard ecological regression analysis. In the right figure, we have filtered away all precincts with less than 10 votes. For example, almost all the precincts circled in green on the left have been removed on the right. These were the precincts that were so small that the top-down results were mostly noise. These points were having a lot of influence on the line of best fit. When you remove these points on the right, you see that the red lines now agree completely with the blue line. Summarizing, we find that downweighting small precincts makes ecological regression robust to noisy census data. This finding is quite robust. It holds for toy down as well as top down. It also holds for another way of downweighting the small precincts, using weighted linear regression based on the number of votes instead of filtering out very small precincts altogether. In every case, the red lines agree with the blue lines. These versions of ecological regression are much more stable than the standard practice. It also holds for much smaller elections. These plots are for Dallas County, which has 2.4 million people. We performed the same experiment with much smaller places, as low as 50,000 people in Galveston City. The results were still the same. You need to downweight small precincts. The conclusion is that we must account for small precincts when doing ecological regression. If we do, then top-down will not seriously affect the racially polarized voting test in Voting Rights Act cases. That is all for today. Please reach out to JN or me with any questions, and find our full paper on FORC for more details.